Tonight, we are going to look at a cosmic sculpture that seems almost too beautiful to be real. It is not a painting, and it is not a computer-generated fantasy. It is a nearby nebula, shaped by dying stars, newborn suns, invisible magnetic fields, and light traveling across space for thousands of years. Recent NASA telescope observations have highlighted how much information can hide inside a colorful cloud. When astronomers combine different wavelengths of light, a nebula stops looking like a soft patch in the sky and becomes a physical landscape, a map of temperature, chemistry, motion, and time. The object at the center of our story is the Helix Nebula, one of the closest and most recognizable planetary nebulae to Earth. Despite its name, it is not a planet, and it has nothing to do with planets forming. The name comes from an older misunderstanding, because through a small telescope the glowing shell can resemble a distant planetary disk. In reality, the helix is the final outer envelope of a star much like our Sun long ago. That star was quietly fusing hydrogen in its core. For billions of years, it followed the ordinary rhythm of a middle-aged star, converting light elements into heavier ones and sending a steady stream of energy into space. But stars do not remain unchanged. As the hydrogen in the core became scarce, the star expanded into a red giant. Its outer atmosphere grew thin and unstable. Pulsations, stellar winds, and changing layers of fusion gradually pushed material away from the surface. The nebula we see today is the result of that gentle-looking catastrophe. Gas has been expelled into space, but it has not spread evenly. Dense knots survived inside the flow, creating thousands of comet-like structures. Each knot has a darker head facing the central star and a long, faint tail stretching away through the surrounding gas. Those knots are enormous compared with anything on Earth. Some are wider than our entire solar system. Yet they are still tiny compared with the nebula itself, and they are incredibly tenuous. A cloud that looks solid in an image is actually a near vacuum by terrestrial standards, with atoms separated by vast distances. The colors provide clues about what is happening. Blue and green light often comes from oxygen and other ions excited by energetic ultraviolet radiation. Redder regions can trace hydrogen and nitrogen. The exact palette in a telescope image may be a sign for scientific clarity, but the underlying differences are real. Different atoms are glowing in different physical conditions. At the center is the exposed core of the former red giant. It is now a white dwarf, a stellar ember with roughly the mass of the Sun compressed into a body about the size of Earth. It no longer creates energy through ordinary core fusion. Instead, it shines because it is still extremely hot, radiating the stored heat left from its previous life. That tiny central star is responsible for much of the nebula's appearance. Its ultraviolet light strips electrons from atoms in the surrounding gas. When those electrons recombine or fall through energy levels, they emit photons at specific wavelengths. In this way, the nebula becomes a giant, natural laboratory for atomic physics. A single image can therefore carry several stories at once. The central point tells us about the star's final transformation. The rings reveal episodes of mass loss. The knots record the interaction between slow, dense material and faster stellar winds. The outer halo preserves traces of an even earlier phase, when the star was losing mass more gradually. This is why modern observations are so valuable. A visible light photograph shows where some of the glowing gas is located, but infrared and ultraviolet observations reveal other layers. Infrared light can expose cooler dust and molecules. Ultraviolet light can show the influence of the hot central remnant. X-rays may reveal shocks where fast winds collide. Combining these views is like studying a city with a street map, a weather radar, a heat camera, and a geological survey at the same time. No single image is the whole nebula. Each wavelength is a different measurement of the same evolving system. The phrase planetary nebula can also be misleading in another way. These objects are not explosions like supernovae. The star is not destroyed in one instant. Instead, its atmosphere is removed in a sequence of pulses and winds. The process is slower, more layered, and in some ways more intricate than a violent stellar blast. Eventually, the expanding gas will become too thin to glow brightly. The white dwarf will continue cooling for immense stretches of time, while the atoms once held in the star's atmosphere drift into the interstellar medium. Some of that material may later become part of new clouds, new stars, and perhaps new planetary systems. That cycle is one of the quiet foundations of cosmic chemistry. The early universe was made mostly of hydrogen and helium, with only small traces of lighter elements. Stars changed that inventory. Through fusion and stellar winds, they return carbon, nitrogen, oxygen, and other ingredients to space. The atoms in a future world may once have belonged to a star that lived before the sun. Carbon in a living cell, oxygen in a breath, and calcium in a bone all belong to a much older story of stars making, mixing, and releasing the materials of complexity. The Helix Nebula is close enough for astronomers to study in detail, but close is a relative word. Its light still needs roughly 700 years to reach us, depending on the distance estimate and the region being measured. When we observe it, we are not seeing the nebula as it exists today. We are seeing an ancient signal crossing the darkness. That delay changes the meaning of the image. The telescope is not merely looking outward. It is looking backward. Every layer of the nebula is a record from a different moment, and the entire scene is a message from a star whose transformation began long before human history. There is also a lesson in the scale of the central white dwarf. The star has lost much of its outer material, but its core remains gravitationally bound. Matter is compressed until ordinary intuition fails. A small volume can contain a mass comparable to the Sun, supported not by normal gas pressure, but by the quantum rules governing electrons. Quantum mechanics is therefore present in the final glow of a star. The same physics that describes electrons in atoms also determines how a white dwarf resists further collapse. On the scale of the nebula, we see filaments and shells. On the scale of the core, we encounter matter under conditions impossible to reproduce in an ordinary laboratory. Astronomers can learn even more by studying how the shapes change across wavelengths and over time. Repeated observations reveal expansion. Spectroscopy measures the speed of the gas. Chemical lines identify the elements. Models then test whether the nebula's structure can be explained by a single star, a hidden companion, magnetic fields, or a combination of all three. In many planetary nebulae, a companion star may help sculpt the outflow. A second star can alter the geometry of the gas, creating asymmetry, jets, or rings. Even when a companion is difficult to see directly, the pattern of the material around the white dwarf can preserve evidence of its influence. So the apparent simplicity of a glowing ring can be deceptive. It may be the visible surface of a three-dimensional structure, tilted in space and illuminated unevenly. What looks like a circle in a flat image could contain cavities, lobes, streams, and overlapping shells. This is the larger promise of space telescopes. They do not simply make the universe prettier. They make it more legible. Better resolution separates knots that once blended together. Wider wavelength coverage reveals hidden material. More sensitive detectors allow scientists to follow faint boundaries where the nebula meets the surrounding interstellar gas. And every improvement can change the question. Instead of asking, "What is this beautiful object?" astronomers can ask, "How did each layer form? How fast is it moving? What is the chemistry of the dust? Which structures were made by the star alone, and which required a companion?" The answers matter beyond one nebula. Stars like the Sun are common. Understanding how a Sun-like star ends helps us predict the distant future of our own star. In about 5 billion years, the Sun will expand, shed its outer atmosphere, and leave behind a white dwarf. The details will not be identical, but the broad sequence may be familiar. That future is unimaginably far away, yet the process has already happened throughout the galaxy. Planetary nebulae are not rare curiosities. They are snapshots in a recurring phase of stellar evolution, each one shaped by its mass, rotation, chemistry, companions, and environment. The colors we see are therefore not decoration. They are the visible signature of matter responding to radiation. The arcs are not painted lines. They are moving gas. The dark spaces are not empty backgrounds. They may contain dust, molecules, and low-density material that will only become visible under another kind of light. When we look at a cosmic nebula, we are seeing order emerge from a complicated flow. Gravity holds the star together. Fusion changes its interior. Winds carry material outward. Atoms absorb and release energy. Magnetic fields and companions may redirect the gas. And across all of it, light carries the evidence to us. The final image is quiet because space is quiet. There is no sound traveling through the vacuum, no thunder accompanying the star's transformation. Yet the scene is active on every scale, from the motion of individual ions to the expansion of a shell larger than our solar system. For a few minutes, the nebula can seem like a destination. But it is better understood as a transition. A star is becoming a remnant. Its atmosphere is becoming part of the galaxy. Its chemistry is entering the future. And perhaps that is why these objects hold our attention. They show that endings in space are rarely simple disappearances. A star can fade as a star while its material begins another journey, eventually joining the clouds from which something new may form. The glowing shell is a farewell, but it is also a handoff. In the darkness between stars, the elements continue moving. The universe keeps the ingredients, rearranges them, and starts again. So when the next telescope image arrives, filled with blue light, golden dust, and delicate knots, remember what you are seeing. Not just a beautiful cloud, but a time capsule, a physics experiment, and a preview of the far future of a star like our own. The cosmos is not only vast. It is recycled, layered, and alive with change. And in the fading light of a planetary nebula, we can watch one small star return its inheritance to space.